We already saw vectors briefly when we were finding out how to solve systems of linear equations slightly more succinctly than using the equations themselves, but there's actually a lot more to vectors. So we're going to have a look at those now. They also turn out to be very useful for describing things in 3 or more dimensions. So we often use a single number to represent bits of information about things which only really have one thing attached to them, for example, weight or height or temperature. The magnitude of the number depends on the thing being measured and also the units. Such quantities are called scalars, so they're just a single number that describes something. But there are many times when we would like to describe something that needs more than one number to represent it. For example, if you want to describe the wind, then you need, for example, how strong it is and what direction it's blowing in. From physics, you'll know that force has both a magnitude and a direction. Velocity has a magnitude and direction, and also sound. It has the loudness, but also the direction. So each of these things has a magnitude and a direction, and if a quantity has a magnitude and a direction, we call it a vector. So scalars only have one number that describes them, but vectors have a magnitude and a direction. We'll often represent vectors as an arrow or a directed line segment, where the length is telling us about the direction the direction is given by the direction and the length tells us about the magnitude. So we could have a vector like so, which we're going to label as A with a little arrow on top. And as we mentioned previously, textbooks will often use boldface for vectors, but that's hard if you're writing. A vector has a start point, which we will call the tail, and it has an end point, which we will call the head. Things that it's worth noting about vectors. Vectors contain no information about the starting point. They really just say how far you go from any given point. Which means we can interpret them as displacements, instructions how to get from some starting point to another point. However, if we assume a starting point, then we can interpret vectors as points. So we're going to come to that in a moment. Let's work in a coordinate system. We'll use R2 for the moment and then head into R3. Then we can describe a vector obtained by moving A1 units in the x direction and A2 units in the y direction using this notation. So we've got little angle brackets, and this says go A1 units in the x direction and then A2 units in the y direction. A1 and A2 are called the components of our vector A, and sometimes you'll call them the x component and the y component. So if we consider the little vector A given by 3, 2, there are many different representations, because remember, all this vector says is from wherever you're starting with, go 3 in the x and 2 in the y. So if you start from the origin, then if you move 3 points in the x and 3 points in the y, you get to the point 3, 2. But if you start, for example, at the point 1, 3, then your vector says go 3 in the x and 2 in the y, you'll end up at the point 4, 5. And if you start at other points, you'll end up at other points. So really, it's important to remember vectors don't give you a starting point. They just tell you if you have some starting point, where to go from there. So if we're in R3, then obviously our vector needs to have 3 components. It needs to tell you how far to go in the x, y, and z directions. So we would write a 3-dimensional vector as a1, a2, a3, which says go a1 in the x direction, then a2 in the y direction, and then a3 units in the z direction. As we've seen, there are many representations for a given vector. And the point that I said about thinking of vectors as a point comes from thinking about the vector at the starting point of the origin, because then the number of units in the x direction and the number of units in the y direction will take you to the point 3, 2, and 3, 2 were the coordinates of the vector. So this gives us a link between points and vectors. Just to clarify, if we're given some point x1, y1, then the vector x1, y1 is called the position vector of P. It tells you how to get from the origin to the position of point P. Extend this idea to working in 3 dimensions. We would have some point, I'm going to call it P tilde, which is x1, y1, z1. Then the vector, let's call it x2, y2, z2. Then the vector x2, y2, z2 would again be the position vector of P. It would say if you start at the origin and you move x2 units in the x, y2 units in the y, and z2 units in the z, you will end up at this point P. We can also make a link if we have 2 points in R3, then the vector with the representation given by the line segment between them is x2 minus x1, y2 minus y1, z2 minus z1. It's always tricky drawing things in 3D, so I'm just going to draw this in 2D. If we have our 2 points, so this is going to be A is the point x1, y1, and B is the point x2, y2, then the vector AB is given by x2 minus x1, that should be a square bracket, y2 minus y1. And this is again using our ideas of Pythagoras' theorem, because we want to travel this distance in the x, which is x2 minus x1, and we want to travel this distance in the y, which is y2 minus y1. So we're using right angle triangles. But notice that we could, once we've got our vector, which looks like this, it is a vector. It doesn't start or end at any other at a particular point. So we could have the same vector going from point C to point D. So just as we have algebraic rules for scalars, which you've been using a lot, we have rules that tell us how to add, subtract, and multiply vectors. So we need to have a look at some of those. So to add 2 vectors, we place the tail of one to the head of the other, and the sum is the vector that completes the triangle. Easier seen in a diagram. So we're going to take our vector A. So here's A, and then we're going to take vector B. And remember, vectors can be moved to start any place that we want. And the resulting vector of adding these 2 together is the one that starts at the tail of A and ends at the head of B. So this is A plus B. Obviously, we have the usual commutativity of addition, which means it doesn't matter whether we say A plus B or B plus A. So if you notice, I'm going to start with B, and then I'm going to have A, and when I do my addition of those, so starting at the tail of B and moving to the head of A, I get the same vector here as I got up here by adding A plus B. So if we're working with components, how does this work? Well, it's very convenient. You just add the corresponding components. So A plus B is equal to 2 plus minus 1. So we're adding the 2 to minus 1. And then we're going to add the y components, 3 plus 1, which gives us 1, 4. So we've got a new vector which says go 1 in the x direction and 4 in the y direction. And if you had 3 dimensions, you'd do exactly the same thing. You'd add the x components, the y components, and the z components. We can also scale our vectors. So this is a way of multiplying vectors by a scalar. And this really just is a way of being able to change the length of a vector. So if we have our original vector A, we can also have 2A, which says we want the vector that goes in the same direction, but it has twice the length of A. So this would be the vector 2A, same direction but twice as long. You could scale by something less than 1, so you might have, here's the vector half A, and you can also multiply by a negative, which then flips the direction. So for example, this vector is the vector minus A. We've changed its direction by 180 degrees. Alright, so if we have a vector A which says go 2 in the x and 3 in the y, what are these things? Well, 2A, we just multiply each component by the amount we want to scale it. So it's going to be 2 times 2, 2 times 3, which is 4, 6. And if you were to plot A2, 3 and 4, 6, you'd find that they both point in the same direction, but this one is twice as long. If we do minus A, then we're just going to end up with putting a minus sign in front of each coordinate. So you'd get something in the same direction as this, but just pointing the opposite way. And it shouldn't be a surprise if you do 0.5A, then you're going to have something in the same direction, but half the length. So it's going to be 1 and 1.5. So we've seen addition, which enables us to add 2 vectors, and we've got a way of scaling vectors to get them to point in the same direction but be longer or shorter. And this means we're actually free to also define vector subtraction. And we do this by saying vector u minus vector v is really vector u plus minus 1 times vector v. So if our vectors a and b are as shown, we want to draw a minus 2b. Well, that means a is going to stay the same. I'm going to put a up here. And then we want a vector that is twice as long as b and going in the opposite direction. So b headed up like so. So minus 2b will be something roughly that length and in that direction. So this is a, and this is minus 2b. And now if we add these two, we're going to start from here, go down there, and this is going to be the vector a minus 2b. If we want to do this with components, we've got a vector a which is 2, 3, and b which is minus 1, 1. Then A minus 2B is going to have the components 2 minus 2 times minus 1. So it's going to be 2 minus 2 times minus 1. And our second component will be 3 minus 2 times 1. So that's 3 minus 2 times 1. So if we work this all out, it's going to be 4, 1. So there are practice examples in the homework. It's all quite straightforward, and you'll see some examples where you use 3 components, but it works exactly the same.